kind of lens do you see up on the board right now? Yep. It is convex, also known as converging. Right, convex, converging. I don't really care what you call it. Be prepared to see both names, convex and converging. Why does the name converging come in here? Like, why don't we just call it convex? What significance does the word converging have to this? Yep. Yeah, rays of light will converge as they go through this lens. This horizontal line that's imaginary and goes through the geometric center of this lens, we call the principal axis. Rays of light that are parallel to that principal axis will converge at one particular spot. They'll all come together at one particular spot. What do we call that spot where the rays all converge? The focal point. Now, we're not suggesting that all rays of light converge at the focal point. We're saying all parallel rays will converge at the focal point. This one over here we're going to call 2F. That's just kind of a spacer. It doesn't have any optical significance besides being a spacer for where we put our object and so on. On the other side, we have the same spacers, F and 2F, but I'm not going to label those F and 2F because they're not really, it's not really a focal point on the left side. The focal point is really on the right side. All right, if I want to find what the image of this object looks like, we've got our object on the left-hand side over here. Okay, the object distance. By the way, the object distance is the distance from the object to the lens. The object distance here is greater than 2F. 2F is the distance from 2F to the lens. And F would be the distance from the focal point to the lens. We've got a situation right now where the object is beyond 2F. It's out there. Okay, how far beyond? Doesn't really matter. Okay, it doesn't matter how far beyond it is. The characteristics of the attributes of this image will be the same. The exact size of the image, the exact placement of the image will move, but if it's smaller, it's going to be smaller. If it's bigger, it's going to be bigger. Okay? How much smaller, how much bigger, that depends upon exactly where it goes, but the fact that it's smaller or bigger doesn't. All right, let's draw this out. We did this yesterday, but we'll do it again real quickly here. There's millions of rays of light that reflect off of this object. Okay, the first one that we're going to look at is going to reflect off at the top of the object. Where are we going to draw it? Where's it going to go? Parallel to the principal axis. Good. Now, it truly refracts when it hits the surface, the boundary between the air and the lens, and then it refracts again when it hits the boundary between the lens and the air. But the net effect of that is that it goes the same as if it was going straight to the middle of the lens and then down through the focal point. So that's the way we draw it because it's easier to do it that way. There we go. There's the first ray. There's a million other rays that we can draw as well, but we're going to just draw one of them because that's enough to give me what I want here. Where am I going to draw it? From the top of the object down through the center, right? We call it the optical center of the lens. Okay, when we do that, we find that those two rays converge over here. We draw our image from the principal axis down to where they converge. We're going to make that, we're going to label the three characteristics or the three attributes of that image in whatever order you want. Doesn't matter. Hey, what's one of them? It's smaller, yeah. The image is smaller than the object. You can have trouble determining whether it's bigger or smaller or same size. Take a ruler and measure it. In this case, I think it's fairly clear that it's smaller. Okay, what else? It's inverted, yeah. And the third one, this is the tougher one, but not so bad now because we learned yesterday towards the end of class how to distinguish here. What is it? Yeah, this is real. A real image means that what? It can be projected onto a screen. Doesn't mean we have to, but we can project it onto a screen. And how do we know that it's a real image? This is what we saw at the end of class yesterday. Because solid lines intersect. And we don't have any dotted lines on here, but on one of the ray diagrams, two of the ray diagrams, we are going to have dotted lines. It is a real image, can be projected onto a screen because solid lines intersect. Let's draw the next one here real quickly here. First ray, parallel. Second ray goes, and it continues down through the focal point. Second ray goes down through the optical center. They're going to converge over here. The image is going to be what? It's going to be same size. Image is going to be same size. It's going to be real because it is solid lines that intersect. I'm listing them usually in the same order, right? Real, virtual is listed third here. It doesn't make any difference at all. Yep. And it's going to be inverted. It's going to be upside down. So notice we went from larger inverted real to same size inverted real. You might be able to predict what's going to happen next, even without drawing the array diagram. Larger inverted real, same size inverted real. What's your prediction for the next one? Smaller inverted real. It is going to be smaller inverted real. Let's draw that just to double check though. Parallel down through the focal point, and then we're going to go down through the optical center. And sure enough, I didn't quite draw them long enough to intersect here, but sure enough, it is going to be a larger inverted and real. So smaller inverted real, same size inverted real, and larger inverted real. What's next? There is going to be no image. Okay, we can't go, like we go smaller, same size, larger, like there's no logical thing that comes next. So next logical thing for us is going to be that there's no image. Something's going to change here now, right? Something big is going to change here. There is no image, but let's just draw that just to make sure that you can do that. First ray is parallel down through the focal point. Second ray is down through the optical center. These don't converge on the right side. If we extend them as dotted lines, they don't converge on the left side as well. So there is no image. Now, the last one, we went, remember, smaller inverted real, same size inverted real, larger inverted real, and then something big happens because we've ran out of smaller, same size, larger. Something big happens now, so there is no image. This is the transition to something else happening here. What do you think you're going to get here? This is when you're going to get a virtual image, right? A virtual image. And that virtual image is going to have the characteristics of, oh wait, they don't even converge there. Let's extend them. Yeah, they converge back here. This virtual image is going to have what other characteristics? Right side up and larger, or larger and right side up. Does that make sense? Now, you can draw the ray diagram. Sometimes it's helpful to draw a ray diagram, but you can also, some people find it easy enough to just remember the patterns. Okay, if I remember that it starts off, if I could picture the first ray diagram in my head, and it starts off smaller inverted real, and then I remember the pattern, okay, same size inverted real, okay, larger inverted real. All right, logically there is no image next, and then we go virtual after that. Then maybe you don't have to draw the ray diagrams. I'll tell you that you will never get a question on an exam where you're going to have to draw the ray diagram. The reason we draw them is because it becomes useful for us sometimes to know a characteristic in order to solve one of the mathematical problems. So this is more of a tool than it is a product. If you remember the patterns, that's fine. If you have to draw the ray diagram to figure it out, that's fine. Okay, whatever it is that works for you. All right, what kind of lens is this? This is concave, caved in the middle, right? Thinner in the middle than it is at the edges. What's the other name for it? Diverging, concave or diverging. We drew this ray diagram yesterday in class, and I asked you to draw the last four. I'm not going to draw this one again, nor am I going to draw the last four. I'll pick one to draw. They all end up being the same, right? At least essentially the same. Let's skip forward a couple and draw this one. Here's our object. Our object distance here is bigger than f, bigger than the focal length, but it's smaller than 2f. Right? It's in between f and 2f. First ray we're going to draw is parallel to the principal axis. And where's it going to go? It's a diverging lens, somebody told me. So it's going to diverge away from this point that we call the focal point. It's going to go up. Now, don't draw it like this, because if I draw it like this, like that doesn't diverge away from the focal point. Don't draw it like this. That doesn't diverge away from the focal point. You need to draw it like this. so that if I extend it back, it's going to go through the focal point. That diverges away from the focal point. Now, that second ray, where's it going to go? This is the easy one because same as for the last one, right? Same as a convex lens. It's going to go, yeah, it's going to go through what we call the optical center of the lens right here. Now, we could extend this back like this, but we don't really have to. We know that it's dotted lines intersecting there, which means it is, what are the characteristics, the attributes? It is virtual, yeah. It is smaller, and it is upright. The characteristics of a concave or diverging lens are always smaller, upright, and virtual. Always. So, again, talk about drawing ray diagrams, talk about remembering patterns. Hey, pattern for this one is easy. If you have a diverging lens, it's always the same three characteristics: smaller, upright, and virtual. Draw the ray diagram, remember the patterns and the characteristics. I don't really care, whatever ends up working for you. What I want to do today is do a little bit of math. Mathematically analyze these. So we've graphically analyzed them by drawing ray diagrams. Now I want to mathematically analyze them. There are two equations that we're going to use here to describe these mathematically. The first one is what we call the lens equation. And the lens equation looks like this. 1 over f is equal to 1 over do plus 1 over di. What do you think f stands for? It's the focal length. And the focal length is the distance from the lens, from the middle of the lens, the center of the lens, to the focal point. Do is the object distance, we call it, and it's the distance from the object to the center of the lens. Di is the, Braden, is the image distance. Di is the image distance from the center of the lens to wherever the image is formed. Now, what units do you think we're going to measure these in? Meters? Yeah, that's fine. That's a standard unit, right? If in doubt, always go meters, because meters always works for us no matter what we do, right? But more often than not, we actually use centimeters for this. Why can we use centimeters or millimeters or inches for that matter?
It's because the units are always for the same characteristics.
Yeah. As long as you're consistent here, we get the same units in every term, which means the units end up canceling. Now, I would go with whatever units you're given in the question, but if you're uncomfortable with that because you're so used to converting to meters, then go with meters, because it will work. It just means a little bit of extra work that you don't need to do in these questions. So 1 over f equals 1 over do plus 1 over di, okay, in whatever units you want, as long as you're consistent. Now the other equation, m is equal to hi over ho equals negative di over do. M stands for the magnification of the image. How many people have taken biology? Everybody's taken Science 10. You've used microscopes in Science 10 at least, even if you haven't taken biology. You draw those pictures. Actually, I think now they just have you take photos of them with your phone, don't they? Instead of drawing the picture. But you have to label on it the magnification. It's how big the image is compared to the object, right? The size of the image compared to the size of the object. Think about what I just said. The size of the image compared to the size of the object. What does the word compare mean? Divide, right? The size of the image height, compared to the size of the object, or divide it by the height of the object. What units do you think we have for HI and HO? Anything you want, as long as it represents a distance, like centimeters, meters, kilometers, inches, whatever you want, as long as you're consistent, right? What units do you think we'd have for magnification? Centimeters over centimeters cancels and gives you No units. It's like index of refraction, right? Remember, index of refraction was meters per second divided by meters per second, so there was no units, they canceled. Here we have centimeters divided by centimeters, so they cancel and we have no units. There's no units for the magnification. Okay, when you did this, do your diagrams or took your pictures in biology class and labeled your magnification, you didn't say the magnification was 40 centimeters. You said it was 40. Or you might have said 40x, right? Do you know what I mean there? Okay, which just means times. Okay, that's not actually physics, like physically necessary. In biology, they might make you write the x. Okay, but mathematically, it's not necessary to actually put an x. It's not wrong, but it's not necessary to put it. Di is the image distance. Do is the object distance. It just so happens that the ratio of the image height to the object height, which is the magnification, is the same as the ratio of the image distance to the object distance. There is a negative, though, there. Watch out for that. It's on your data sheet, so you don't have to worry about that. But you need to put that negative in there in order to maintain certain sign conventions. For us, up until now, positive means right, negative means left, or north-south, or east-west, or whatever the case may be. But there is a different sign convention that we're going to introduce with these variables, and that sign convention falls apart if we leave off the negative in that equation. All right, let's complete this table, which is going to give us our sign conventions for each of these variables. The reason I've colored these in this way, by the way, is because you're going to notice that the blue variables, the sign convention follows a pattern. And then the green variables, the sign convention will follow a pattern, but a different pattern than the ones that are in blue. The focal point, the focal length is positive if we have a real focal point. And it's negative if you have a virtual focal point. Now, when do we have a real focal point? When we have a converging lens. Converging lenses cause rays to converge, rays that are parallel to the principal axis, that is, to converge at the focal point. So it's a real focal point. A virtual focal point exists on a diverging lens, because the rays don't really converge at the focal point. They diverge away from the focal point, right? We draw that ray diagram here. That's not converging at any focal point. That's diverging away from the focal point. So converging lens always has a real focal point or a positive F. Diverging lens always has a virtual focal point or a negative F. DO is positive if we have a real object. And it's negative if you have a virtual object. Now, here's the good news for us in Physics 30. It will always be a real object. Now, it is possible to have a virtual object in a lens system, but it has to be just that, a lens system, where you have 2 or 3 different lenses, and the image formed from one lens becomes the object for the second lens. That can be a virtual object. But we're not going to see that. So we don't need to worry about that. For us in Physics 30, DO will always be a positive value. Okay? And it will never be a negative value for us. DI? Well, DI is positive. Take a guess. DI is positive if the image is real. And when is the image real? Well, that's when it's sometimes useful to have that ray diagrams, those ray diagrams, right? It's real when we have an object on a convex lens, an object that is beyond 2F, at 2F, or in between F and 2F. Then it becomes no image, and then it becomes a virtual image, and then for the diverging lenses, it's always a virtual. So it's sometimes we're told in the question whether it's real or virtual, sometimes we're not. In that case, we have to look at the ray diagram or remember the patterns to determine whether it's a real or virtual image. So it's positive if you have a real image, and it's negative if you have a virtual image. And there's no rules as to, always this or always that. You just got to think about the ray diagrams. All right, let's fill in HO and HI here now. HO is positive if the object is upright. So green doesn't refer to real or virtual. Green is referring to right side up or upside down. It's a positive height if the object is upright, and it's a negative height if the object is inverted. It would be pretty rare to see the object upside down, but we could. It's possible. What do you think I'm going to fill in for the image height here? The image is going to be, image height, HI, is going to be positive if the image is upright. Now, I usually put M kind of outside of the table. It's virtually the same rule as for image height and object height, but not quite. Magnification is positive if the object and the image are on the same side of the principal axis. In other words, if they're both upright, M is positive. If they're both upside down, M is positive. Right? If they're both on the same side of the principal axis, in other words, both upright or both inverted, M is positive. If one of them is upright and the other one is inverted, M is negative. Now, don't get mixed up here with magnification, okay? Some people look at it and say, oh, if I get a magnification of 0.5, that means it's upside down. No, it doesn't. 0.5 means the image is half the size of the object, and it's upright. Well, or at least they're both on the same side of the principal axis, and since the object is usually upright, that probably means the image is upright as well. If I get a magnification of negative 0.5, then that means the image is upside down, and because it's negative, and the image is half the size of the object. If I get a magnification of 2, the image is twice the size of the object. If I get a magnification of negative 2, then the image is twice the size of the object and upside down, or at least flipped over relative to the object. Now, lots of things to remember there, but there's clear patterns, right? The first equation, the sign convention relates to upright, or relates to right, real. Say this right one of these times. The first equation, the sign convention, relates to whether it's real or virtual, and then the second equation relates to right side up or upside down. Does that make sense? Okay, we're going to do a couple examples. One right now. This is example 1 on the handout that I gave you earlier on. It says a converging lens of focal length 24 centimeters is used to view an insect 18 centimeters in front of the lens. We want to determine the image distance and the magnification. A converging lens. I'm going to circle that. Every time I see a lens or a mirror, which we're going to do in a few days here, I'm going to circle it and draw attention to that. How come? Why is that important? Yeah. Yeah, it's concave lens if you draw your ray diagram. I don't think I actually need to draw a ray diagram for this one, but it's certainly never wrong to do that. Biggest thing for this is converging lens always has a positive focal point. Now, if I forget that this time, I'm going to get away with it, right? But if I have a diverging lens and I forget, then I'm not going to get away with it. Converging lens, positive focal point, 24 centimeters. Let's just say F is 24, positive 24. It's used to view an insect 18 centimeters in front of the lens. What is that? that DO or DI? It's DO. The insect is 18 centimeters in front of the lens. We want to find DI, the image distance, and we also want to find the magnification here. So let's do this. Okay, looks like FDO, DI, looks like I'm going to use the lens equation. If you want to try the magnification equation first, go ahead. There's only two. Let's fill in our numbers here. 1 over 24 is equal to 1 over 18. I can use centimeters here, right, because I'm being consistent at least, and the units cancel. Oh, who's good with fractions? One of you is good with fractions, I guess. Okay. Well, here's the good news, and it frustrates me, and it bothers me that this is the good news, but in the end, physics is about the thinking and the solution, and it uses a lot of math, but it's not about the math. So if we have a trick, we'll use it. And we have a trick. So if you're not good with fractions, it bothers me that you're not good with fractions, but we're still going to do the trick to get you out of that little problem, okay? Take your calculator. Everybody do this with me, okay? Take your calculator and do this. Repeat after me. Let's say 24 x to the minus 1. That's, well, you don't actually physically have to repeat after me, but with your fingers, repeat after me. 24x to the minus 1, which is 1 over 24. Okay? Now, I got to take 1 over 18 over by subtraction, right? So 1 over 24 subtract 1 over 18. Make sense? Press enter. Is that my answer? Nope. What's that represent? That would be 1 over di, right? So flip it over. Negative 72 is my answer there. You see what I did there? 1 over 24, take away 1 over 18. Okay, and that gave me, this gives me, what was that? Negative 0.0139 equals 1 over di. I just skipped a step there. But then when I solve for di, di is 1 over negative 0.0139. So all I'm going to do is take this number, flip it over, and I end up getting 72. Now you can find a common denominator and do your thing, whatever, or you can just take about 6 seconds on your calculator and get negative 72. Oh, forgot to put in the negative there, actually. Does that make sense? Does that make sense?
Yeah.
Okay. Let's find the magnification. Mathematically, this is actually easier. We're going to say negative di over do. It's also hi over ho, but I don't know what hi and ho are, right? So I got to use this. Negative di, negative 72 centimeters divided by 18 centimeters, right? I think that gives me 4, doesn't it? Or negative 4 it is, right? No units, is that right? It is positive 4, you're right, because it's negative 72, right? It's negative di, and di was negative 72. So watch out for that as well. You might say, well, what difference does it make? I get 4. I would have got negative 4. I would have got the same number, right? What difference does it make? Well, what if they asked you whether it was right side up or upside down? They didn't. But if they did ask you if it was right side up or upside down, we get an answer now that is right side up. Before, we had an answer that was upside down, which is wrong. Good? I'll tell you what, let's do one more example right now, and then I'll let you work on 1 or 2 questions here. And then we'll see if we have time for the third example here. Second example, number 2. says an object located 32 centimeters in front of a lens forms an image on a screen 8 centimeters from the lens. Determine the focal length of the lens and the attributes of the image. Why am I circling that? Good. It's formed on a screen. It doesn't say it's a real image directly, but indirectly it does, right? If it's on a screen, the image is real. That means that DI, the image distance, is positive. Does that make sense? That's what we're telling you in this question by saying it's formed on a screen. DI is real, DI is positive. An object distance is 32 centimeters. The image distance is positive 8 centimeters. We want to determine the focal length and the attributes. We'll worry about the attributes in a moment here. 1 over F is equal to 1 over DO plus 1 over DI. 1 over 32 plus 1 over 8. You can find the common denominator if you want. Do your thing that way. Or you can just say 1 over 32 plus 1 over 8. Enter. Then what? Inverse of that, 1 over that. We end up getting 6.4. And it's positive. 6.4 centimeters. Okay, what about the attributes? Larger, smaller, same size. That's the hardest one, I think, actually. Let's leave that till the end. Is it right side up or upside down? Oh, that's kind of tricky as well, actually. Is it real or virtual? It's real. We already identified that it's real. Ironically, the most challenging thing is actually the easiest part of this question. How do I identify whether it's right side up or upside down, or bigger or smaller? I could calculate magnification. I don't need to actually calculate it, though. Okay, if I divide negative something by positive something, I'm going to get negative something, which means it's inverted, right? And if I divide 8 by 32, whatever that works out to be, I know it's smaller than 1, so the image is smaller. Like if you want to actually calculate magnification, go ahead, but it's not necessary here. You can just look at the equation. Yep. I know it's inverted because if I divided negative 8 divided by 32, I get negative 0.25. The negative tells me that the image and the object are flipped over from one another. So assuming the object is right side up, then the image has to be upside down. Remember, if we go back to the table, magnification is positive if the object and image are either both upright or both inverted. It's negative if one's upright and one's inverted. We got negative. So one must be upright, one must be inverted. We're going to assume the object is right side up and the image is therefore inverted. And the fact that it's 0.25 tells me that it's smaller. That make sense? All right, let's have a look at your worksheet.